Hello, and welcome to presentation Extended Reality and Empathy in the Era of Generative Artificial Intelligence. My name is Denis Gracanin, and I am an associate professor in the Department of Computer Science at Virginia Tech, United States. My research interests include human-computer interaction, extended reality, generative artificial intelligence, Internet of Things, and cybersecurity. This presentation describes some recent work conducted in collaboration with my students and colleagues. This presentation is divided into 5 segments. The first segment describes the topic and provides the motivation for empathy-enabled extended reality and introduces the concept of generative extended reality, Gen XR. The second segment discusses psychophysiological signals and illustrates how to integrate large learning models with psychophysiological inferences. The third segment discusses the use of generative artificial intelligence technologies. The fourth segment presents 2 use cases, and the final 5th segment includes discussion and acknowledgements. Recent advancements in generative artificial intelligence, Gen AI, have significantly transformed multiple domains. A major claim about extended reality is that it can foster empathy and elicit empathetic responses through digital simulation. Empathy is defined as an ability to understand and share others' feelings, a critical part of meaningful social interactions. Empathy-enabled extended reality combines these 2 views and provides a 2-way empathy link between users and extended reality. The availability of portable and affordable biosensor, especially contactless, makes it feasible to measure in real time physiological and other signals by using extended reality. An instrumented physical space enriched with a variety of sensors can provide a lot of measurements about the user and the surrounding physical environment. These measurements, such as heart rate, breathing rate, facial expression, electrodermal activity, EEG, eye tracking, and others, can be used to inform, potentially in real time, about users' cognitive and emotional state, in other words, inference, and enable empathetic responses and measurements. This information can be used both to evaluate the impact of extended reality content on users and to adapt extended reality content based on user state, in other words, feedback. The data about users, especially cognitive state and stress level, can direct how XR content are presented and interacted with. The environmental and physiological data can be combined with self-reported data to create the contextualized data about the user. This contextualized data then informs the stimuli, XR content, that is provided to the user. Empathy is the ability to understand and share others' feelings, and we have 3 different types of empathy. That includes cognitive, emotional, and compassionate empathy. In cognitive empathy, we simply know how the other person feels and what they may be thinking. In emotional empathy, when we feel physically along with other person, as those emotions are contagious. And then finally, compassionate empathy, when we understand the person's predicament and feel with them, but we are also spontaneously moved to help if needed. So now if we look at those 2 types of empathy, it will be interesting to have some manifestation of that empathy in XR systems. So therefore, that relationship between XR and empathy can be explored from 2 points of view. First, we can view XR as an empathy machine that elicits or triggers empathetic responses in users. And second, we can view extended reality XR as an empathetic entity that empathizes with user and adjusts XR user experience accordingly. So therefore, an empathy-enabled XR system should support both views of both perspectives. The environmental data then provided by, let's say, wearable sensor, Internet of Things in an instrumented physical environment can then inform about the physical world and surrounding the subject or subjects, and therefore a physiological data will provide an insight into the cognitive state, such as stress, affect, and activity. And then we can also have cognitive data provided as direct input from the subject or gathered indirectly, let's say from social media, let's say Facebook or X posts, and that will provide information about current mood or perhaps even emotional mental state. So now, with the data collected from a variety of sources, including wearable, mobile, and embedded devices, and correlated with social media posts and activities, including social interaction in the physical world, can be then used for inferencing about user state. Human physiology and psychology are intricately linked and profoundly influence each other. So, in that context, we would like to use or develop methods for estimating psychological states from peripheral physiological signal, and that whole process or approach is called psychophysiological inference. We would like to build on, or we need to build on these inference results and develop more advanced prediction models. In doing so, we can start by using basic electrodermal activity and electrocardiogram data, and with that we can determine valence and arousal. However, multimodal psychophysiological data can be used to predict varied psychological states and monitor overall emotional and cognitive well-being. With such information as an input, Gen AI techniques and methodologies, for example, LLMs, large language model, can demonstrate remarkable proficiency in processing complex linguistic structures and producing text that resonates with human-like coherence and relevance. Enhancing LLM's ability to interpret mental states could make them more adept in applications such as psychotherapy, which would benefit from emotional understanding. Large learning models, LLMs, are designed to understand and generate human-like text and can mimic empathy. But LLMs, of course, don't actually feel emotions. However, LLMs can be trained, customized, and integrated with multimodal human data to help LLMs understand human thoughts and emotions. Such empathic LLMs could be useful in applications such as customer service, education and training, virtual assistant, and psychotherapy. Empathic LLMs can predict user physiological states from psychophysiological data used by the deep learning model to generate crafted prompts for the LLM. LLMs have emerged as transformative tools in the field of psychotherapy and offer unique opportunities to provide users with personalized mental health support. As an example, a small pilot study with 8 participants used a chatbot that passively monitors user stress throughout the day using physiological data collected by a wristband device, and actively interacted with participants at the end of the day based on how much stress they had experienced. The results of the stress prediction model from physiological data show that 6 out of 8 participants experienced some stressful events in their workday. The predictions are consistent with the findings of the short stress states questionnaire, indicating that the stress prediction model is more likely to predict the stress state of engagement. With empathic LLMs predicting user psychological states from psychophysiological data, we can use those predictions as an input to enhance user experience by providing relevant and meaningful interactions and customized content. Generative AI key technologies include, in addition to LLMs, vision language modeling, text to 3D, text to speech, and others. So therefore, in that context, Gen XR can be viewed as a context-aware recommender using generative AI for real-time content modification. Based on that, we propose a generative XR framework that uses artificial intelligence for dynamic and context-aware content creation in augmented reality. By integrating vision language models, the XR system detects and understands the physical space around the user, recommending contextually relevant objects. These objects are transformed into 3D models using the text to 3D generative AI techniques, allowing for real-time content inclusion within the augmented reality space. This approach enhances user experience by enabling intuitive customization through spoken commands while reducing costs and improving accessibility in order to advance AR interactions. The vision and language capabilities support the generation of comprehensive and context-specific content that can be impacted by psychophysiological data. We can also incorporate multilingual speech-to-text translation. This multilingual support helps to overcome the limitations of current text-to-3D models and LLMs, which primarily support only English, while also enabling easier communication with the system compared to multilingual text input in augmented reality environments. Moreover, we employ multilingual text-to-speech translation to communicate with users in their preferred languages, creating a more inclusive and seamless interaction experience. We can leverage the advanced capabilities of LLMs to recognize objects from speech inputs and suggested related objects. This functionality enriches the user experience by offering contextually appropriate enhancement and alternatives, fostering dynamic and engaging augmented reality environments. Additionally, using semantic search through vector database, we can efficiently retrieve objects based on the user's interaction history and current context. This method prioritizes the reuse of existing objects, reducing the need to generate new ones, and thus conserving GPU resources. By allowing users to access previously generated objects, it also mitigates the challenges of obtaining consistent results with diffusion-based models, where users might experience varying outputs even when using the same prompt. The efficient use of the database enhances system responsiveness and resource management in the augmented reality environment, addressing a critical bottleneck that was identified in prior work. To address these challenges and explore potential benefits, we explored the use of the framework in various settings. User can customize extended reality, or in this case, augmented reality environment, based on the recommendation from the LLM or VLM or repository object, as well as object detected in the physical environment. We can see an example of a common dining kitchen area where various objects were recommended and created or retrieved in real time. The created content is then appropriately positioned. For example, a coffee mug object and a real-world coffee machine aligned properly in space. The task performance evaluation demonstrated the system overall efficiency and usability in various settings. So to summarize, the benefits include enhanced immersion due to interaction with the customized content, enhanced user control because of the control over customization, as well as accessibility, since the content can be also informed by psychophysiological data. The first use case is an immersive virtual reality digital twin used in the context of cybersecurity education for water treatment facilities. The goal was to explore the utility of a generative XR system to leverage digital twin concept and to integrate Internet of Things devices. The domain-specific knowledge was effectively specified and integrated with AI agents to address design challenges and to enhance performance for this specialized application. In addition, a controllable mini-physical model of a water treatment facility was included. The model can be viewed from within a fully immersive environment by using several camera feeds. A short video illustrates user interaction with an AI agent, including camera feeds.
Hello. Welcome to the practice phase, where you will be able to walk through some tasks and experience various types of cyber attacks. My name is David Smith, and I am a cybersecurity and digital twins expert who will be guiding you throughout this process. The practice phase contains 5 different scenarios where you will be tasked with identifying and classifying attacks. Each scenario represents one particular stage of the water treatment plant. To get started, use your left controller to hit the Y button. This will open up a camera view of the physical side of the digital twin. You should use this tool to verify that the tasks performed in each scenario are reflected in reality.
The second use case is a fully integrated extended reality pulse simulator system used to investigate the impact of haptic, audio, and visual feedback in an extended reality training medical simulator. The hardware component provides the haptic feedback using a 1 degree of freedom force feedback device. The developed simulator provides haptic, auditory, and visual feedback of the pulse of a trauma patient. The participant experience higher immersion and perform better in the simulator's scenario. The qualitative feedback of the user shows that the extended reality system also allowed the efficient utilization of working memory resources. The finding underscored a fundamental aspect of human cognition, the brain's remarkable ability to adapt and allocate resources within working memory based on sensory input. The findings can also help to address challenges in designing immersive, multimodal, collaborative generative XR system and to better understand the impact of cognitive load. Recent advancements in generative artificial intelligence have significantly transformed multiple domains and have created many exciting research opportunities. Generative artificial intelligence key technologies include large language model, vision language models, text to 3D, text to speech, and others. With that in mind, generative extended reality system can be viewed as context-aware recommenders that use generative artificial intelligence for real-time content modification, while at the same time providing empathy machine and empathetic entity perspectives. Empathy-enabled extended reality system utilize empathic large language models to predict user psychological states from psychophysiological and other data. Empathic large language models predictions provide an input to generative artificial intelligence technologies to enhance user experience by providing relevant and meaningful interactions with customized content. Such system can be used in many applications, including education, training, and healthcare. We need to fully utilize the tremendous growth potential for generative extended reality systems and applications. I would like to acknowledge contributions and participation of my students and colleagues as follows. Psychophysiology finding, Purvesh Dongre, PhD student, Virginia Tech. Generative artificial intelligence finding, Majid Behravan, PhD student, Virginia Tech. Immersive digital twin use case, Anthony Lee, master student, Virginia Tech, and Mohammed Azab, associate professor, Virginia Military Institute. Multimodal interactions use case, Nikita Chandrasekhar, PhD student, Virginia Tech. Thank you for your attention.